Today, we're taking you into a world where simple rules create surprising complexity. Imagine a checkerboard of tiny lights where each light decides whether to turn on or off by looking at its neighbors. No central conductor, no grand plan, just little local decisions. Yet out of those simple steps, whole patterns bloom, swirl, crash, and stabilize. This is the universe of cellular automata, and the most famous example is Conway's game of life. The question we explore today is, can a modern AI model learn those simple rules well enough to predict what happens next, even when we withhold key details about the board it plays on? And if it can, what does that tell us about intelligence, prediction, and the limits of computation?
Every so often in science, you find a system that is so simple to describe that it almost feels like a toy until you watch it move and realize it's hiding something deep. Cellular automata are exactly that. Think of a grid or a patchwork quilt. Each square is a cell that can be in a state like 0 or 1, off or on, dead or alive. At each step in time, a cell looks at the 8 squares around it. This is called the Moore neighborhood, and it updates its own state according to a simple rule that depends on those neighbors. That's the entire recipe. But when you run it, you get this astonishing menagerie of behavior. Little creatures that glide, blinkers that pulse, spaceships that drift across the board.
And the game of life, just to put some pins on the board, has a very specific set of rules. If you're a live cell, think of a light that's currently on. You stay alive if you have 2 or 3 live neighbors. You die if you're lonely, with fewer than 2 neighbors, or overcrowded with more than 3. If you're a dead cell, light off, you become alive, you are born, if you have exactly 3 live neighbors. That tiny rule set gives rise to the famous glider, which looks like a little arrow that scoots diagonally, the blinker, which is a line that flips direction every step, and much more.
Here's where the new twist comes in. A recent study trained a transformer model. Think of the family of neural networks behind many language tools to predict the game of life's next state in one step. The researchers call their model LifeGPT. It's a decoder-only transformer with 2 important ingredients: rotary positional embeddings, often shortened to ROPE, and forgetful causal masking, or FCM. The key claim is that LifeGPT is topology-agnostic. That means the model isn't told the size or shape of the grid, or even the boundary rule that says what happens at the edges. Instead, it learns from examples, and it ended up being able to compute the next global state with near-perfect accuracy, even when the board wraps around like a donut. That's a toroidal grid.
We're going to unpack that gradually. First, a couple of quick definitions to make sure we're all walking together. Topology in this context is about the shape of the board and what happens at the borders. If you imagine an ordinary board, when a glider reaches the edge, it just falls off. But with toroidal boundary conditions, the top wraps to the bottom and the left wraps to the right. It's like Pac-Man. Leave one side, appear on the other. The idea that a model could learn what to do at the edges without being told is pretty striking.
Now, what's a transformer in plain terms? It's a type of neural network designed around attention. Instead of reading data strictly left to right, it can look across the whole sequence and decide which parts are relevant, updating its internal representation based on those selections. A decoder-only transformer is a version that produces output 1 token at a time, conditioning on what it has already seen. This is the same family used in many text generation systems. Rotary positional embeddings, ROP, are a positional encoding trick that helps the model understand where tokens sit in a sequence in a way that can generalize across lengths, almost like giving the tokens a compass that keeps their orientation meaningful even as the map gets bigger. Forgetful causal masking, FCM, intentionally hides some past tokens during training, encouraging the model to sometimes look further back instead of just relying on the most recent bits. It's like periodically closing your near pages in a notebook, so you practice recalling the older notes too.
What did the researchers actually feed into LifeGPT? They took pairs of game boards, an initial condition, often called an IC, and the next game state, an NGS, in one step. Because transformers expect a sequence, they flattened each 2-dimensional grid into a 1-dimensional string of numbers. They placed that string into a formatted prompt and tokenized it. Tokenization just means turning text into integers a model can process. The model learns to predict the next state string given the initial state string, one token at a time.
The paper pays particular attention to the training data. If you always show the model dense patterns, it will mostly learn what to do when lots of cells are alive. If you only show sparse patterns, it may get good at predicting lots of zeros. To measure that, they use the order parameter, written as eta, the Greek letter A, to mean the fraction of cells that are 1s in an initial condition. So I near 0 means almost all dead. I near 1 means almost all alive. E around 0.5 is maximally mixed. They tried two strategies. One was high entropy, where Y hovered around 0.5, like flipping a fair coin for each cell. The other was broad entropy, where they deliberately sampled ICs across the full range, from all dead to all alive, so the model would encounter every corner of rule space often enough to learn it.
And the results showed that breadth matters. With the broad entropy set, the model achieved near-perfect accuracy on single-step predictions across the board. With the high entropy set, it did fine on many cases, but stumbled, especially when it came to the birth rule, the condition where exactly 3 live neighbors bring a dead cell to life. Because that happens less frequently in dense random boards, the model didn't see it enough to master it, and its accuracy dipped on sparser inputs. It's like learning a language. If your lessons never include the past tense, you'll have trouble when someone asks you about yesterday.
It's worth pausing on what accuracy meant in this study. During training, they used cross-entropy loss, which is a standard measure of prediction error. But for evaluation, they periodically froze the model, fed it a set of test initial conditions, some random, some famous patterns like the glider, hammerhead spaceship, blinkers, and the R pentamino, and counted how many cell tokens in the next state were exactly correct. That's an intuitive metric for listeners. Of the 1,024 cells on a 32 by 32 board, how many did the model get right for the very next step?
And then they explored sampling temperature. This is a knob that controls how deterministic the model's output is. A temperature of 0 means always pick the most likely next token, no exploration. Higher temperatures, like 0.5 or 1, inject variability so the model can sometimes pick a slightly less likely token. This is essential for creative language generation, but not so helpful when the data itself is deterministic. Predictably, LifeGPT's best accuracy came with temperature 0. At higher temperatures, a little more error crept in. Even so, after sufficient training, the model's accuracy remained extremely high across temperatures.
Let's talk about the claim that this model is topology-agnostic. The training examples included toroidal grids, those wraparound boards. The model wasn't explicitly told, hey, this is a donut, so edges connect. Instead, it inferred the behavior from patterns. If a cluster near the right border interacts with one near the left on the next step, the model sees that correlation and internalizes it. The authors also trained a variant, LifeGPT multigrid, on multiple grid sizes at once, tiny boards of 2x2, 4x4, 8x8, and 16x16. The model continued to make near-perfect one-step predictions across all those sizes, which suggests it latched onto the local neighbor rules in a way that didn't depend on a particular board size. That's the heart of the topology-agnostic idea. The rules are local, and the model learns them from data, not from built-in geometry.
What happens when you ask the model to go beyond one step? The authors tried what they call an autoregressive loop. That's just a simple trick. You feed the model an initial condition, it predicts the next state. Then you feed that output back in as the new input and ask for the next, and so on. It's the same whisper-down-the-lane approach used in language generation, but now applied to a grid. The paper found that small early errors sometimes snowball a few steps later, causing the model's predicted evolution to diverge from the true game of life. This is exactly what you'd expect in a chaotic system with sensitive dependence. Change a single cell, and given enough time, the pattern can unfold in a different way. In other words, multi-step prediction is hard, even if one-step prediction is superb.
There's a fundamental idea under that difficulty called computational irreducibility. It's the notion that for many systems, cellular automata are classic examples. There's no shortcut that tells you what the system will look like far in the future, except by simulating each step. You can't jump ahead. The authors don't claim their model breaks that barrier. Instead, they show that the model learns the local update rule very well, and so produces excellent single-step predictions. And then, like any simulation, it can be stepped forward. An occasional error in one cell at one step can propagate across time. That's not a failure of the idea so much as an affirmation of how these systems behave.
Let's walk through a few of the building blocks again in plain language, because they're not just technical extras. They're part of why a language-style model works on a grid. Attention is the mechanism that lets a transformer consider relationships across a sequence. If our flattened grid is a long line of tokens, attention can make it easy for a token corresponding to a cell to look at tokens corresponding to its neighbors and any other relevant context. Rotary positional embeddings, ROP, give the model a flexible sense of position so that patterns seen in one part of a sequence can generalize to another part or another length. And forgetful causal masking, FCM, keeps the model from overfitting to just the most recent context during training. It occasionally hides some of the past tokens it would normally see. That encourages broader attention and, in this case, sped up learning and improved performance at higher sampling temperatures.
There's another subtle piece: how the data was prepared. Because transformers consume sequences, the 32 by 32 board was flattened into a line. That could have been a problem because two cells that are neighbors in 2D might be far apart in the 1D sequence. But attention doesn't care about distance in the line. It can connect any two positions. That's part of why using a transformer makes sense despite the mismatch in geometry. It's a different way to get spatial relationships compared to a convolutional neural network, CNN, which hardwires locality through sliding filters. CNNs have historically performed well in this domain precisely because they embed the idea of a grid into their architecture. Here, the transformer didn't need that inductive bias. It learned the neighborhood logic from the data itself.
On the evaluation side, the researchers did something that will make anyone who has ever built datasets nod. They carefully constructed test inputs that the model had not seen during training. They estimated the size of the possible initial conditions as 2 to the 24. That's a 32 by 32 grid of binary choices, an astronomical number. They trained on 10,000 samples, which is a microscopic slice of that space. Then they tested on other samples, including those classic patterns like the glider and R pentamino. Getting near perfect, one-step predictions on that kind of held-out data is a sign that the model didn't just memorize, it learned the rule.
Now, there were some telling cases in the multi-step experiments. A single-cell misprediction early on, one cell being alive when it should be dead, for instance, led to divergence from the ground truth a handful of steps later. The glider and R pentamino were among those examples. The takeaway is not that the model is brittle. Rather, in a system like this, everything is connected step over step. That's also what makes cellular automata such rich test beds for studying the limits of prediction. Even perfect knowledge of rules doesn't make the far future easy to foresee without marching through time.
Let's zoom out and compare this with some of the other approaches in the field. Researchers have used convolutional neural networks to learn game of life, sometimes with explicit design choices that mirror the CA's structure. There's also a thread of work using algorithmic information theory to discover rules from data, an approach that perturbs a system and estimates how its algorithmic complexity changes to tease out causal structures. And a particularly creative direction is neural cellular automata, where the update rule itself is a small neural net, and you train it so that, starting from a seed, it grows into a target pattern, say the shape of a flower, over many steps.
This study sits in that landscape as a clean demonstration that a relatively modest transformer, not a gigantic one, can learn local rules from flattened grid data without being told the geometry. The key innovation is the training data design, the broad entropy set that supplies a spectrum of initial conditions, and the use of ROP and FCM to stabilize and improve training. It's a nice illustration of how, for certain problems, you can lean on attention to recover structure you didn't explicitly encode.
You might be wondering, why does any of this matter beyond being a neat trick? One reason is that many real-world systems look like cellular automata when you squint, local interactions giving rise to global patterns. Think of fire lines in a forest, traffic jams forming and dissolving, recrystallization in materials, or even aspects of biological growth. If an AI can learn the effective local rule from observational data, say a time lapse of a field spreading or a tissue developing, it could give us a way to make short-term predictions, or to explore what-if scenarios by tweaking the initial condition and letting the rules play out.
There's also the idea of coarse graining. Even if we can't know every fine detail of a future state, we might be able to predict it at a lower resolution, the overall shape of a spread, the broad distribution. Prior research has shown that complex cellular automata sometimes admit simpler descriptions at a coarser scale, a bit like blurring a high-resolution photo to reveal its larger forms. A model like LifeGPT could be repurposed, perhaps, to output coarse-grained forecasts where exactness isn't possible or necessary.
The paper also connects to a lively debate about whether neural networks can help us navigate around computational irreducibility. The sober answer here is not in the general case, but you can find what the authors call pockets of reducibility, places where the system's behavior has enough regularity or symmetry that a statistical or learned shortcut works for a while or at a certain scale. In practice, this means a model like LifeGPT might be a powerful assistant. Flawless for one-step transitions, robust for a handful of steps, and useful for guiding intuition even when exact long-term predictions remain out of reach.
We should talk about two forward-looking ideas the authors raise: reinforcement learning and world models. Reinforcement learning is a framework where an agent makes decisions and gets rewards or penalties. It's transforming how language models play strategic games, for example. How would that apply here? Game of Life is a zero-player game. No agent acts after setting the initial board. But you can imagine a metagame. Propose next states, get rewarded when they match the true next state, and explore actions that minimize long-run divergence. Reinforcement learning could guide the model to prefer choices that keep future predictions consistent, even if there are multiple plausible immediate outputs.
World models, meanwhile, are internal representations of how a system works. In language tasks, the absence of a grounded world model sometimes leads to hallucinations, confident but incorrect statements. In LifeGPT's case, a world model could be an explicit internal representation of the game of life rule. A separate module that says, if a dead cell has exactly 3 live neighbors, it becomes alive. If a living cell has 2 or 3 neighbors, it stays alive. Otherwise, it dies. You could imagine training a hybrid system that not only predicts the next state, but also predicts or verifies the rules used, using the rules as a check to catch errors before they propagate. In other words, the model might learn to reason about the rule and police its own outputs.
There's a fascinating philosophical question tucked in here as well. The game of life is Turing complete, meaning with the right configuration, it can perform any computation a general computer can. Transformers, on the other hand, are only Turing complete under idealized assumptions we don't have in practice, such as infinite precision in positional encodings. So, could a perfect LifeGPT simulate an arbitrary game of life computer forever? Probably not under realistic constraints, but that mismatch is an opportunity, using systems like Life as a testbed to probe what modern AI architectures can and cannot compute and how close learned approximations can get in discrete rule-based worlds.
We should take a moment to be clear about the limits noted in the study. First, while the model is described as topology-agnostic, the experiment centered on small square toroidal grids, 2, 4, 8, 16, and 32 per side for training and testing in different runs. The claim is strongly suggested by the results, but not proven across arbitrary shapes, large sizes, or higher dimensions. Second, the rules tested are just the binary game of life. There are many other cellular automata with different rules. Some might be easier or harder to learn. Third, multi-step prediction does sometimes diverge due to single-token errors, especially for patterns where small clusters of live cells exist near the edges.
On the flip side, the model's learning is remarkable given its tiny view of the universe of possible inputs. Remember that 2024 number? Training on 10,000 examples is vanishingly sparse in that space. The model's near-perfect one-step performance on unseen configurations underscores that it really did learn the rule. That's an important proof of concept for using transformers as general learners of local dynamics from data.
I'm thinking about concrete analogies for listeners. Imagine each cell is a house on a block. Every night, a housekeeper looks at the 8 nearest houses, the neighbors on all sides and the corners, and decides whether to leave the porch light on. If exactly 3 neighbors have their lights on, a dark house turns on. If a house is already lit, it stays on if 2 or 3 neighbors are also lit. Otherwise, it goes dark. There's no city planner coordinating it. Yet when everyone follows the same rule, patterns move across the neighborhood. Little groups that coast, lines that blink. LifeGPT is like an observer who's watched many nights, and when you show it a snapshot of the neighborhood tonight, it can tell you what the lights will look like tomorrow, almost perfectly across many neighborhoods, even if we didn't tell it the exact size of the city or that the east edge wraps around to the west.
And the twist with autoregression is that if that observer misreads even one porch light one night, maybe mistaking a reflection for a light being on, then for the subsequent nights, the prediction can drift. That's not because the observer forgot the rules, it's because that mistake changes how neighbors decide, which changes the next change, and so on. Sensitive dependence is the phrase here. Small changes can lead to big differences over time.
Let's also touch on how the training was orchestrated. The model used cross-entropy loss, which in plain terms penalizes the model when it assigns low probability to the correct next token. It was optimized with Atom, a standard gradient-based method. Rotary positional embeddings were turned on, and forgetful causal masking was applied with a probability around 0.15, meaning some past tokens were randomly hidden during training to encourage the model to consider broader context. Early in training, the loss fell quickly, suggesting the model was learning. Crucially, the researchers report that validation loss remained independent because the validation set was separately generated, and the chance of accidental overlap was effectively 0.
The sampling temperature tests give a nice practical hint for people who might use similar models. In deterministic tasks, keep your temperature low unless you have a reason to explore. In this study, temperature 0 was essentially always best for accuracy. Higher temperatures made tiny deviations more frequent. There's an intuitive analogy. With a cooking recipe, if your goal is to reproduce a dish exactly, you follow the instructions closely. Low temperature. If your goal is to be inspired by a dish and make something new, you improvise. High temperature. For CA next step prediction, we're in the follow the recipe camp.
There's a lovely statistical footnote in the paper about the data distribution. Because the high-entropy dataset was generated by flipping a fair coin for each cell, the fraction of alive cells, EI, follows a binomial distribution centered at 0.5 with some spread. That means the model saw far more mid-density boards than very sparse or very dense ones. A broad entropy dataset deliberately equalizes exposure across the whole range from 0 to 1. So rare events, like a dead cell with exactly 3 live neighbors in a very sparse board, aren't rare anymore during training. That's what made the difference for learning all aspects of the rule.
Let's connect back to cellular automata and artificial life, A-life. A-life is a field that studies lifelike behavior using computational, physical, or biochemical tools. The game of life belongs to a tradition of soft A-life, purely simulated systems, for exploring emergence, self-organization, and pattern formation. There's a fascinating mutual influence currently unfolding. Researchers have argued that large language models could be used to run A-life experiments, creating open-ended environments, evolving agents, and that A-life might in turn help us understand how language models themselves exhibit organization and collective behavior. LifeGPT adds a new angle, a transformer becoming a reliable operator for a classic A-life system, even hinting at how we might control or steer such systems by learning their rules.
I also want to briefly mention a related theme in the paper, algorithmic information theory, and efforts to extract rules from data. Some prior work proposes measuring how the complexity of a system changes when perturbed to reconstruct its causal structure. That's a different but complementary approach to what LifeGPT does. One tries to infer rules by looking at how description length or algorithmic probability behaves. The other learns a predictive mapping from a large number of examples. Both are part of a larger program. Can we move from watching complex systems to explaining and predicting them in a principled way?
For listeners wondering about extensions, the authors sketch a few. First, they suggest training on many different cellular automata rules, not just life, sampling a tiny region of what some call the rulesset, the space of all possible rules, so the model learns to identify which rules best match observed data. Imagine feeding it a video of a slime mold growing on a petri dish and asking, which local rule CA best approximates this? Second, they propose embedding rule representations into the model as a world model, letting the model double-check its predictions against the rule. And third, they suggest reinforcement learning loops that reward consistency across multiple steps, potentially reducing the cascading effect of early errors.
There's an ethical dimension to flag as well. If a model can learn to control or design cellular automata, altering rules or initial conditions to produce target behaviors, then it becomes a powerful lever for creating emergent phenomena in simulation. That's a sandbox with creative potential, but it's also a reminder that steering complex systems requires humility. You might think you're shaping one outcome, but the system's richness can produce side effects. The authors nod to the need for oversight and thoughtful design if we extend these tools toward real biological or ecological systems.
Before we close, let's revisit the headline results in compact form. LifeGPT, a decoder-only transformer with rotary positional embeddings and forgetful causal masking, learned to predict the next state of Conway's game of life on toroidal grids with near-perfect accuracy when trained on a broad entropy dataset. It didn't need explicit instructions about grid size or boundary conditions. It inferred those from data. When used in an autoregressive loop, it could simulate multiple steps, though occasional early errors sometimes caused divergence, consistent with the known sensitivity of cellular automata. A multi-grid version trained on multiple board sizes performed near perfectly on all included sizes, suggesting the model internalized local rules in a topology-agnostic way.
And the big picture meaning, this work is an example of finding pockets of reducibility in a hard problem. We don't get a magical way to skip to the 10,000th step, but we do get a compact model that captures the local rule faithfully and can serve as a fast, flexible engine for simulation and exploration. With careful training data design, especially covering the full spectrum of initial conditions, a transformer can recover and generalize the logic of a two-dimensional cellular automaton from sequences alone.
If you're someone who works with complex systems, there's a broader lesson here. Sometimes, instead of encoding all your domain knowledge into the architecture, you can let attention do the heavy lifting, provided you feed the model the right variety of examples. Transformers won't always be the best tool, but when locality is a pattern to be discovered, not told, they can be surprisingly adept learners.
And perhaps the most encouraging part is that this wasn't a billion-parameter behemoth. The model was modest by today's standards, trained on a single workstation GPU, and yet the results were striking. It suggests that for well-chosen tasks with clear local structure, we may not need to scale to the moon to get useful, precise behavior.
I'll leave listeners with an image. Picture that checkerboard of porch lights at dusk. The rule is local and simple. The chorus is emergent and beautiful. You don't need to know the exact dimensions of the neighborhood or whether the blocks wrap around. By watching enough nights, you can learn the rule and say, with confidence, what tomorrow's pattern will look like. But as days pass, the whisper of one wrong light can ripple out. Prediction remains a dance between what you know now and what the system's richness will make of it.
So today we learned that LifeGPT, built on attention, rope, and a touch of forgetfulness, can learn the game of life's local logic to near perfection, provided you show it the full tapestry of possibilities. We learned that broad training data matters, that deterministic tasks prefer low sampling temperature, and that multi-step forecasting in complex systems remains a delicate business. And we learned that these models can be bridges. From rules to predictions, from observations to explanations, from simple local interactions to the unfolding of complex worlds.
If you're curious to go deeper, the authors have made their code and data available. But even if you never write a line of code, there's something delightful in knowing that a modern language model can sit with a two-dimensional grid, listen carefully to the quiet talk between neighbors, and say, almost flawlessly, what comes next.
That's our show. Thanks for listening.